This is Calculus AB 2015 AP exam question number 6. It says, consider the curve given by the equation. Here's the equation right here. It can be shown that dy dx is equal to, and here's an expression for the slope function on this curve. Okay, so the first part here says, write the equation for the line tangent to the curve at the point minus 1, 1. Now, when you want to write the equation of a line, you need two things, basically the slope and a point. We already have the point, and you can get the slope from various methods, but here they give us the slope function, so we need to know the slope at this point, so we're going to just use that. So we're going to set up, so here's dy dx, and what I've done sometimes is people get a little confused on how they plug things in, so I'm just putting everything I'm going to substitute for, I put a parentheses around it. So this is the same equation as the one they gave us, but I just put a parentheses around the y's and the x's because I'm going to substitute. And you shouldn't really have to do that, but if you get confused, do that. So y is 1, so I'm going to plug a y in for 1, and x is minus 1. And so here's the equation. So now I just plug them in. Now, this is the equation. This right here is the slope function for anywhere on this curve, any place. And now we want the slope at a particular point. That at this point, that's when we plug in the values for x and y into the slope function. And if you just plug them in, you end up getting this is 3 minus the plus, so it's 1/4. So the slope on the curve at this point is 1/4. So next thing they want us to write the equation of the line. Now, you could write it in y equals mx plus b form, but that's a little harder and a little more work. It's not a big deal, but you want to save time on an AP exam, so you want to do things the quickest way. If you know this point slope form of the equation of the line, it's really very simple. And most of us say, well, I don't know that equation, I have to memorize it. Well, you sort of don't. You sort of do know the equation, because if you know the slope equation, so I'll develop it for you here, and you'll see how easy it is, I hope. So here's the slope equation. Slope is change in y over change in x. We learned that in Algebra 1 very early on. Okay, and change means the difference between the 2 points. So change in y, so here's a change in y over the change in x, and I'm calling this xp. So in other words, you used to see it as y2 minus y1 over x2 minus x1. Now this is going to be our xy coordinate, and this is the point of the x and y coordinates. And now the only thing you have to do, if I know this equation, that's the point slope form of the equation of a line. Here's the slope and here's the point. I just have to move this up to the other side, multiply both sides by x minus p. And then what I do is, so here it is, multiplying both sides by x minus xp, excuse me. And then what I just do is I'm going to add yp to the other side. So there's the equation of the line. And so all I have to do is plug in m, x of p, y of p, and it's done. So those are the three things I have to do. So I wrote my information here. Here's my point, minus 1, 1. The slope is 1/4 at that point. And so now here's the equation I have here. So I just recopied this equation here over here, but I did the same thing. I put a parentheses around each thing I'm going to substitute into. Now, you don't have to do that, but if you get confused, then it's something you need to do until you stop getting confused. But for the m, I'm going to put 1/4. That's what m is. And the reason I do that is for here, people get screwed up with the signs here. It's x minus x point, and x point is minus 1. So it's x minus minus 1, and then I plug in a plus 1 for the y point, and that's your plus 1 there. And then I'm just going to clean this up a little bit. You don't have to do much with it. I just don't like two signs in a row like this. So it's 1/4 of the group x plus 1 plus 1. And you don't have to do any more with that. That's the equation of the tangent line at that point. Now what I've done here, let me show you, give you a little visual here. This is a curve. This is not a function now. You notice they don't say it's a function. It's a curve. And you can tell it's not a function because for any value of x, I should only have one value of y if I'm just visually thinking of the vertical line test. And if I take this value here, x equals 10, you can see there's 3 points. So it only has to happen at one place. So this is not a function, it is a curve. Okay, and this is what it looks like. This is this curve right here. And I have here, and you can see I can move, I drew a little sliding tangent here. Okay, and just to see, and you can see the slope is changing. these are the coordinates, x and y coordinates, and as the x and y coordinates change, the slope is changing. It's just a little of interest here. You don't need to do this, but it's just kind of nice to see what's going on sometimes. And if you look, if I move it to the point minus 1, 1, now it's at the point minus 1, 1, you see the slope is 0.25, which is what we came up with in part A. He says, find the coordinates of all points on the curve at which the line tangent to the curve at that point is vertical. Let's do a little, what I'm doing here is I just sketched another function. It's just a semicircle. And for ease, because it's very easy to see where there is a vertical tangent or where there's a horizontal tangent, okay? And just to get a feeling for this, it has nothing to do with this function here, but it just gives an idea about vertical tangents, horizontal tangents. Now you see here the slope, here's the slope function for this curve. This is a semicircle, and the slope function would be minus x over y. So up here when x is equal to 0, you can see the slope is 0. That's a horizontal tangent, okay? And as it moves around, the slope is changing. And if I come down here, you'll see that the slope is going vertical, okay? And that's where you'd have a vertical tangent. So where do these come about, okay? So when we have a vertical tangent, like right here, okay, you see the slope's gone to infinity. The slope is, you see it was vertical. And what's going on then is that the denominator, y is equal to 0. So when you have a vertical tangent, the denominator of the slope function has gone to 0. And the same thing on this side here. See, at this point here, we get a vertical tangent again. The y coordinate is gone to 0. Okay, so the y value is equal to 0. So when you have a vertical tangent, the denominator is equal to 0. And when we have a horizontal tangent, like up here, there's a horizontal tangent, then the x-coordinate is gone to 0. Okay, so the value of the x-coordinate right here is 0. And that's where you'd get a horizontal tangent. So when the numerator is equal to 0, we have a horizontal tangent. And when the denominator is equal to 0, we have a vertical. Remember, numerator is equal to 0 is a 0, so that's equal to 0. And when the denominator is 0, then the function or the slope function is undefined, or it has become a vertical tangent. Okay, so hopefully we have an idea what's going on now. So for this function here, if we want to know where there's a vertical tangent, that means the slope function, the denominator, must have gone to 0 or must be equal to 0. So that's the first thing we got to do then, is we set that equal to 0. So I set the denominator, 3y squared minus x equal to 0. And then I realized you could just solve this for x. So there's x. Now the problem with this is there's two unknowns. And if you remember back in the Algebra 1 classes, when you had two unknowns, you needed another equation. So basically we want to solve a system of equations. Well, we do have another equation. Actually, there's a lot of solutions to this. In other words, if y was 1, then x would be 3, would be a point. If y is 2, x would be 24 is another point. There's a lot of solutions to this right here. But be very careful. See what it says here? It says points on the curve. So they must satisfy this equation. They must be on this curve. And that's our other equation. So we have a system. So what we're going to do now is, so I'm just going to go ahead and take this here. So there, I wrote this equation over again. You see it right here. But what I did to help us, I put a parentheses around the x because I'm going to substitute for x. And if you get in the habit of doing that, again, after a while, you won't need to do that anymore because you won't be making mistakes any longer. So what I'm doing is I'm putting 3y squared in for x. So here I'm going to substitute for x. I put 3y squared in for x. And then what I just have to do is go ahead and start to clean this up. So my next step is I just multiply here and I get minus 3y cubed. So I have y cubed minus 3y cubed equals 12. Group like terms, minus 2y cubed equals 2. Y cubed divided by minus 2, y cubed equals minus 1. And the cube root of minus 1 is minus 1. So there's my y coordinate. And if you remember when you solve systems, once you find one of the values here, you plug it back into one of the original equations. You can plug it into either one, but this one is easier. Okay, so I plugged the -1 into this equation. I wrote the equation over again, and I plugged -1 in for y, and then I get 3. So the point is 3 minus 1. So basically what this is saying is there is a vertical tangent at the point x equals 3, y equals -1. And that is our answer. The tangent line is vertical at that point. X is 3, y is -1. Here's the points they gave us. They gave us 1 point for setting the denominator equal to 0. So even if you're not sure what to do sometimes, always do what you think of. The denominator's got to be equal to 0 for the slope function to be undefined or vertical. And then you write 1 point you got for the equation in one variable. Means you had to know enough to substitute into the curve and get any of these would be correct. You have these three right here have an equation in one variable and then 1 point for the coordinates. So there's your 3 points there. Now let me give you a little visual on this one also. So here, this is the same curve that we have here. Here's a slope function. And again, as you can see, as I move it around at any value of x, here's the value of x where I'm located. Here's the slope at that point. And if you can see what happens is, as I get close to the point 3 minus 1, which is right over here someplace, you see that the tangent line is going vertical. Right? And that's what this question is saying. And now I'm going to move it right to that point, and you can see now that the slope at the point 3 minus 1 has gone to infinity. And you can see the tangent right there. Part C says to evaluate d squared y dx squared at the point on the curve where x is -1 and y is 1. So here we have the same curve. This is the first derivative, which remember gives us the slope on this curve at any point. And the second derivative talks about concavity of the curve, whether it's concave up or concave down. Okay, so what we need to do then is to find the second derivative, we have to differentiate the first derivative to get to the second derivative. So differentiating this is simply the second derivative, but to differentiate this, we have to use the quotient rule. So just a little refresher on quotient rule, because a lot of people make mistakes with this. And so that if I have the quotient of two functions here, and if I want to differentiate this, if h is equal to the quotient of f divided by g, then h prime, I have to use the quotient rule. And the problem where everybody makes a mistake is because this is a negative, a lot of people get these two terms backwards. So here's a little way I remember how to do it so I don't get these backwards. I always start with the denominator. So it's going to be denominator squared and then denominator. This way I know which term comes first. So I put denominator squared times then it's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. This way I don't get them backwards. So again, denominator squared, denominator times the derivative of the numerator. So let's look at this here. So now I'm going to differentiate this implicitly. So the derivative of the first derivative is the second derivative, and then differentiating this using the quotient rule, it's the denominator squared. So here's the denominator squared, and then it's the denominator times the derivative of the numerator. And remember, we're differentiating with respect to x, so this is going to be dy. The derivative of y with respect to x is dy dx. Then minus the numerator, which is y, times the derivative of the denominator. Now what I'm doing is I got to be careful to use a chain rule, and I always try and use a chain rule every time so I don't forget it. So if I'm differentiating the denominator, it's going to be 2 times 3y to the first, which is 6y, and then the derivative, using the chain rule, the derivative of y with respect to x. So I need that in there, and then minus, and then I'm just doing this to give you an idea so I try and use a chain rule every time so I don't mix up. So this is the derivative of x with respect to x would end up just being 1. So I can clean that up in the next step. Normally I don't write that, but I'm just kind of showing you so that I think it through every time. Now if you notice also, I put parentheses around all my terms I got to substitute in for. We don't really care what this function is. We want to know the value of this function at this point. So we don't have to clean this up anymore. actually that's easier rather than cleaning up algebra. At this point, since we only want to know the value at this point, we can plug in these values right off the bat and get it right away. Now, the other thing too is we need to know dy dx, but it's dy dx also at this point. And hopefully you remember that you don't have to redo it again. That is we did this in part A. So we don't want to redo this again. We need to know that dy dx at the same point here, minus 1, 1 is a quarter. So what I'm going to do now is I'm going to substitute all the values in. So for the y, it's 1. Y is 1, so every place there's a y, I put a 1. X is minus 1, so plug in minus 1s for x. And then for dy dx at this point, this is at this point here, I'm plugging in 1/4. So I substitute all the values in there. Now again, on an AP exam, if I'm really stressed for time, I'm not going to waste a lot of time doing, if this is a lot of arithmetic, I'm not going to go ahead and do this because this would only be 1 point. If I'm going to lose 10 points on the next question for 1 point here, I'm not going to do that. I would take my loss here because it's a lot of time. And a lot of times you might get the correct answer for this because it is arithmetically correct. It's just not simplified. So I would take my chances and leave this and go on to the further part of the exam. So here we're going to simplify it now. So this is going to be 1 squared is 1, 3. 3 plus 1 is 3 plus 1 times a quarter minus, and this is 1 times this, so this is no big deal. This is 6/4, which is 3 halves minus 1. And it's over the denominator, which is 3 plus 1, that's 4 squared, which is 16. So now I have that. So this is going to be 4 times a quarter, which is 1, minus, this is 3 halves minus 1, which is 1/2. So now I have over 16, and 1 minus a half is a half over 16. Now what I'm doing is I'm just rewriting this because people get a lot of times make a mistake on this also. This is a half divided by 16, which is the same as 16 over 1. So if you make this mistake, do this, and when you get the idea, then you don't have to do this anymore. So when I do division of fractions, I invert and multiply. So it's 1/2 times invert 1 over 16, so it becomes 1 over 32. So this is the value of the second derivative on this curve at this point, minus 1, 1. And so here's the value, here's what they gave you the points for. They gave you 4 points for this question, 2 points for implicit differentiation. So you got to make sure you use the quotient rule, and I'm sure they're looking forward that you did the chain rule in these parts right here. And then you got 1 point for substituting. Well, 1 point for substituting a quarter for dy dx at that point. And then you get 1 point for the answer, which is 1 over 32. Okay, let's look at visual. Let's go back to this curve. Again, it's the same curve. And now I have the second derivative. Okay, the second derivative of this function at whatever value of x I'm located at. And you can see the second derivative, the point is changing as I move around, and the second derivative is changing. And if I go to the point, let's just go to the point minus 1, 1, right here you see that the second derivative is what we got in this last part, part C, 1 over 32, which is 0.013125, and that's what it says it is right here. Now let's just think about what that means also. Remember, second derivative tells us that the curve is concave up. Now, if you notice, it's sort of hard to tell here a little bit, and because the second derivative is very small, but it is positive, so it's concave up in this region. And notice what happens when I move over here a little bit, it is now concave down because the second derivative is negative. So what does that tell us? That also tells us that there's a point of inflection someplace in here because it changed from concave up to concave down. And that point of inflection is right over here when x is 0. It's at the point 0, 1.26 is the point of inflection where the second derivative is equal to 0. And another thing you should take note of, because this is kind of important and it's used at times, when the curve is concave up, the tangent line is below. Now it's hard to tell because it's very small values, but the tangent line is below. And when the curve is concave down, it's really hard to tell here, but the tangent line is above. It's easier to see down here. See, the curve is concave down because the second derivative is negative. You can see the tangent line is above. Over here, the curve is concave up. Second derivative is positive, so the tangent line is below. That's all. It's a good stuff to keep in mind and understand. Okay, just a reminder, when you're doing AP questions on your own for practice, make sure you look at the solutions they give you. Even though sometimes you get the correct answer, if you don't write it the right way, you will not get full credit. So learn to look at their solutions and what they give you the points for. That's very important. Okay. Now I'm going on a little further with this because there's some interesting things going on with this curve, and I'd like to look at these things, and you may be interested in them yourself. Okay. So here's the curve right here. So I have the curve right here, and I just wanted to see that this is the slope function to this curve. Now a lot of times they will not give you the slope function possibly, so they might ask you questions about the slope at a certain point on this curve. So you have to know enough to differentiate this and how to differentiate it. So if I'm going to differentiate this, remember I'm differentiating with respect to x. So I have to be very careful here. So I'm going to show you how I would do it. So the derivative is going to be 3y squared, and I always make sure I use the chain rule. So this is going to be 3y squared times the derivative of what's inside with respect to x. So it's 3y squared dy dx minus, now I'm using the product rule here. So again, I'm going to use the chain rule each time. It's x times the derivative of y with respect to x plus y times the derivative of x with respect to x. Now again, I normally don't write this, but I make sure I think it so I don't forget it. And the derivative of a constant is 0. And now you just go ahead and clean this up a little bit. So the whole idea is get your dy, this is 1, so don't get confused there. So I get my dy dx terms together. So I just distributed the negative through first, and then I go ahead and bring my dy dx terms. Here's these two terms of dy dx. So I get 3y squared minus x, and I brought this y to the other side, added y to both sides. So dy dx, you just divide by this. And you see I get the same thing that they gave us, which is good. Now, the other thing I noticed when I was doing this, the constant is sitting over here. So this constant could be any value, because think of it. If I differentiate anytime a constant, derivative of a constant is 0. So remember, so there's going to be a whole family of curves. So if I had y cubed minus xy equals 10, when I differentiate, I'd get the same slope function. And there's going to be a whole family like that. For any constant here, that would be true. So in other words, if I just set this equal to some constant, anytime I differentiate this, no matter what this constant was, I would get the same slope function. So there's a whole family of curves. And so remember, if I was to integrate this here by using separation of variables and to find the function, when I integrate, I would get a constant of integration because I wouldn't know which curve I was talking about here. And I went a little further than that because this is pretty interesting. What would happen if the constant was equal to 0? If the constant was equal to 0, I'd get simply y cubed minus xy equals 0. And then I could bring the xy to the other side, and I just switch sides here and divide by y. I get x equals y squared, which is a parabola facing to the right. So here would be this would be true if the constant was 0. So this is one of that family of curves here. And here's a bunch of solutions, which is kind of neat. This is the curve that we had in this problem. The red one is the constant 2. This purple one here with its branch down here, these two pieces here, are the constant would be minus 2. And this light blue one here, the curve here, and its branch over here would be the constant 1. This green one with its branch over here would be the constant minus 1. This one here is plus 1. This one is minus 1. So there's this whole family of curves. And the other thing I wanted to do too is just to see interest, I just varied C for a whole wide range of values. So this is what it would look like for C less than 0. I'm going to get this whole family of curves. You see, there's about 20 curves in here. They're just stacked up, and you can see these two in between here. So this was when c was -1. This curve here was when c was -2. Okay, and there's this whole family of curves. Now, if I let c be greater than 0, you'll see that it'll cover this bottom region down here, and I did this in black. So all these black regions, you see all these different curves in here. They're all one after the other. They go from like probably 0.1 up to about, I don't know, 10 or something like that. And this would be this light blue in here would be when c was equal to 1, and this red one here was when c was equal to 2. And that was just for interest, but it's kind of neat to be able to see these kind of things.